Okay, so we're going to talk about two sample hypothesis testing today. I'm going to do a couple notes, or a couple of problems on the notes, and then we're going to do an assignment, work on it. But I wanted to go over something I saw from a couple people who turned in the assignment already, that one proportion assignment, was solving for the greater than problem. And so let me just draw a picture of it. So here's your null hypothesis, here's your p hat or whatever, and we're trying to solve for this percent. So when you got the z-score for this, you're gonna get a positive number. Let's just throw out a number, positive 2.5. When you look up this value in the z-table, it's going to say something like 0.9523, something it's going to be 9 something. This is not your answer. This 9 value is this less than number. So remember, when you're doing greater than hypothesis testing, we're trying to get the greater than number. So you have to take this and you have to do 1 minus that value, and that would be 0.4 something. So I saw some common mistake. The greater than, it's going to give you a high value. You have to do 1 minus it because we're looking for the greater than number. The z-table always gives you the less than. So that's an important note there. And just a reminder, when you're doing a not equals to problem, so not equals to is trying to get the percentage both less than and greater than. So when you get your value, let's say that this was 0.04, you have to double it, both of them. Then your value would be double of it. So the not equal to is you have to do it on both sides, is the difference. You have to double your answer. Yeah, so just a reminder on the greater than here is that you should probably never get a value that's 95%, for a hypothesis test. Because that means it was almost 100% guaranteed that it's not less than. So something's off if you got this high of a value, probably. The question probably wasn't right. Were there, before we do our problems, did y'all have any questions? If you try the worksheet, have those. All right, maybe I can look at those later. All right, so what we're going to do is we're going to do a hypothesis test for who's more likely to go to prom. So we actually did this doing a confidence interval, if you remember. And so we did this exact same problem with confidence intervals because a confidence interval and a hypothesis test are they're basically, they could go over the same things. They just tell you, the n tells you, confidence interval gives you a range of values that you think it is. A hypothesis test tells you whether this value was plausible or not, gives you, is the alternative likely to happen or not. But so you can do the same problem with confidence intervals and hypothesis tests. So today we're going to do the hypothesis test. And it does have a little wrinkle that we've got to pay attention to. So our problem is we had 50 juniors, 28 out of 50. So I'm going to go ahead and, or maybe I'll do I'm going to write this first. So the sample proportion, and we did this on on Tuesday. Is that right? Yeah, on Tuesday we did when you're doing two samples, I need to distinguish which one's which. So on this one, juniors and seniors, I'm just going to say P of J, P hat J, because J is obviously seniors, was 28 out of 50 are planning on going to prom. which comes out to like 56%, so 0.56. And the sample proportion of seniors was 29 out of 45, which is like 64%. All right. So does this provide us convincing evidence that a higher proportion of seniors are going to prom than juniors? All right. So it looks like seniors from our sample are more likely. Does this provide convincing evidence? Like, based upon this sample size, is this enough evidence to say for sure if seniors are more likely? So we're going to do a null and alternative hypothesis where I'm going to write what P means. So P means the percent attending prom. That's what P is talking about in this example. Percent of juniors, percent of seniors attending prom. Alright, so on two samples, it's important that like our null is that we are gonna assume that these two samples are gonna be equal, and then the alternative is what we're thinking, where we're testing, do seniors more likely. So what I'm gonna do is that I think the proportion of juniors is equal to the proportion of seniors. I'm always gonna have those two samples be equal for the null. So proportion juniors equals proportion seniors. And so then my alternative, P, J, P, S, we think seniors is higher, so I think P, J less than proportion of seniors. This is, you could have easily written these the opposite way, like P of S greater than PJ, PS equals PJ, like it's the same, those are the same things. You can write it either way. Okay. Alright, so here is a major thing that we need to talk about for two samples. So when I'm going to test this, I'm going to go under the assumption that this is true, that juniors are equal to seniors. So actually first, let's do the difference, like what is the difference between juniors and seniors? So the sample proportion of juniors minus the sample proportion of seniors. I could do seniors minus juniors or juniors, it doesn't matter. I'm gonna get, in this case, when I do juniors minus seniors, I'm gonna get negative 0.08. If you did seniors minus juniors, you would get positive 0.08. You're gonna get the same answer, just in a different, the way it's symmetric, it doesn't matter. So this is this. All right, but I'm gonna go, so this is my sample. My sample tells me that seniors are more likely by 8%. But we need to go under the assumption, so we need to assume that P1, or that the proportion of juniors equals the proportion of seniors. So the way we do this is I need to come up with a P to where these are the same. So there's actually on your formula sheet, so let me point this out here. So I'm on the back side with our proportions area. So we have this special thing. We have this special thing for, this is for when we're assuming the null that the two P's are equal. I need to do this thing called proportions combined, where, so it says PC. C means I'm combining them. I'm basically going to get an average of like, where's my middle, to where I can set them to be equal, like the same number. So I'm gonna set these to be the same. So like, I need to get a P combined with these two. Like, what's gonna be my combined thing to where I can say this is like PJPS, to where they're the same. So the formula sheet says I do, where's that? Click it, right? All right, it says I do x1 plus x2 over n1 plus n2. So what that means is I'm going to do 28 and then 50 plus 29 plus 45. So like juniors, seniors, junior sample, senior sample. That's what that is. So when I do that, I get 3 over 5, which in decimal form is 0.6. So this is like my, if I was to actually have them be equal, the ones where they're equal from the sample is, the middle ground is 60%. Like, we're going to go under the assumption that the true value of both of those is 60%. So like, I get the samples, and then I kind of, this helps me get like a middle ground between them. And so this is going to be like our assumed true proportion. So this right here is what we're going to use as our assumed true proportion of juniors and proportion of seniors for this like 2 sample stuff. So this is only for like 2 samples. So like, this is like my proportion, or my sample proportions, but then this is going to be like what we're assuming is the true juniors and seniors. It's just to, like, otherwise we would have no value to set up for those. Okay. So, yeah, we're just gonna use those. Alright, so since this is like our first time doing this little part, our conditions are still the same. I'm just not gonna, that's a bad precedent, but oh well. I'm just not gonna do them on this problem. We'll do it on the second one. But our conditions are the samples random? Are they less than 10% of the population? N times P greater than, so I would check those and see if they check out. But I'm gonna try and just focus on this new part here for this one. Okay, so what's our mean and what's our standard deviation? And so let me go back here. So here's the mean. The mean of the sample proportion difference is supposed to equal what we think the true proportion is difference between the two. So what we did, so what we have here, dang it, okay, so the mean of the proportion of juniors minus the proportion of seniors equals what we think the true proportion of each of those is. And so this is what we're going to assume the true proportion is for both of them, because we're under this assumption right now that this is true. So I'm going to use like 0.6 minus 0.6, and I think the true difference between them is 0, because I think they're equal. So the mean should be 0. Like if I think the proportion of males and females at this school is the same, when I subtract them, they should be 0. The difference should be here. So like my picture is centered around a difference of 0. And my sample proportion was a negative 0.08. If you're like our sample of juniors minus seniors was all the way over here at negative 0.08. So we're going to try and find how likely was this to happen. What percent chance was me getting this far away? What's the percent chance of this happening? Okay, so this is like the difference, and if we're going under the assumption, that these are equal, the difference should be 0. That's why we got this value here. If we're going under the assumption that they're equal, the mean should be 0 every time. Okay, the standard deviation is going to be, let me go back to our formula. So the standard deviation is going to be this formula. And what we use as the p's, the two p's is this combined value is what we plug in for the p's. Like that's still our assumed p for both of them. So it's kind of weird, but it works. Once you understand like this is just plugged in for p, wherever you go, you just plug it in like here. So let me try and get back here. So what we would do, our standard deviation, use a different color. So our standard deviation is supposed to be the proportion of juniors times 1 minus the proportion of juniors. But we think it's the true proportion, which we said is 0.6. So I do 0.6 times 1 minus 0.6 over the sample size of juniors, which is 50. And then the formula says do the proportion, the true proportion of seniors, which we're going under the assumption that it's 0.6, 0.4 over the sample size of 45. So just let me point these out again. Like these values right here are equal because we're under the assumption that the proportion of juniors equals the proportion of seniors. That's why I'm going with these values instead of using the 0.56 and the 0.64. So instead of using these, I'm using this value because I'm saying that they're equal. So you can get kind of confused on this part. Okay, so like the standard deviation when you do that is something like 0.101. So this, the standard deviation is that. So that's like a typical, this is our typical value from the mean of 0. Okay, so we're going to try and find how likely, what percent chance do I have of getting this value of negative 8%? Like seniors were more likely by 8%, given this information. Okay, so then I'm going to do a z-score. So negative 0.08 minus 0 divided by standard deviation, 0.101. You get negative 0.792. So the z table goes to 2 decimals, so 79 would be a good z-score. 0.79. If you did this value, you could also do it over here at positive 0.8, and you'd get a z-score of positive 0.79. So either way, you're still going to get, like, because it's so symmetric, you're still going to get the same answer, whether you did juniors minus seniors or seniors minus juniors. That's why I said it didn't matter earlier. All right, so you get your value in the table. So we look it up, negative 0.79. 0.2148, I think. 0.2148. That's the probability. This is this probability of happening. Less than. All right. So then we gotta conclude. So then 0.2148 compared to the alpha of 5%. So we did not reach that alpha. We were greater than it. So like that means that this value, this 0.8, was likely enough to happen just by random chance. By doing another random sample, juniors could be higher than seniors. Seniors could be higher than juniors. So because this value was likely enough to happen by chance, that means that I don't have evidence. I have no evidence for this. So that's what I'm going to say. I have no evidence, so I have no convincing. And so you say convincing because this means like statistical. You could say I have no statistical evidence, no convincing evidence that the alternative is true. So that the proportion of seniors attending prom is higher than juniors. So like our sample with that small of a sample size, that big of a difference of 8% more with seniors was likely enough to happen by random chance. So that's like saying me flipping a coin 100 times, I could get 55% heads. That could happen by chance alone. So that's like this. Like I had no convincing evidence. Like this was just random chance that seniors were that much higher than juniors. Is all that means. So if I kind of take us back. So like I set up, the null is that they're equal. The alternative is what we thought. So a big difference here is since we're going under the null that they're equal, I have to do this whole combined business. And that's what I'm going to go under the assumption that those are the true juniors, true seniors for like the rest of the problem. So then I use that for the true proportion of juniors, the true proportion of seniors. I use that here. And so then it sets up a problem, a standard deviation, and you solve. So this whole difference with the average being in play is the major difference here. What's going on?
It was a bird.
Upper.
Actually, there was 2 birds.
Oh, no.
Yeah, they were on the
birds.
window. Yeah.
A
I looked
bird.
left and then looked
I
at
know.
you. That's it.
All right.
We weren't just staring at you, Audrey.
Okay. So I'm gonna do another problem together, and then there's 2 old AP stat question free response problems that y'all are gonna do that are 2 samples.
Ew.
So like, they were problems on the 2015 and 2012 or something like that test. So, all right, so let me do the check your understanding. And so this is where you kind of got to keep pace with like where we've been. So if you feel like you're starting to fall behind a little bit, like come and get help from me so you can catch up, because now when we throw in this new stuff, like the combined stuff, you might be like confused. But if you're tracking, you could understand it. All right, so let's try this one out. This is talking about like people who attend preschool versus no preschool, and what effect it has on like their needs later in life. So they recruited 123 children who never attended preschool. They randomly assigned 62 of these children to attend preschool, and 61 of them that would not go to preschool. So 62 get to go, 61 didn't get to go. So maybe I'll do like p hat of school, p hat of like no school, I guess. What they said is that 38 of the children who were in preschool group and 49 of the people who didn't needed social services 10 years later. So like they needed help in some sort of way later, like their development, like these people, only 38 needed help, 49 needed later. So it was 38 out of the preschool group, which was 62. And this one was 49 out of the non-preschool group of 61.
Why did you do the hat on one and the squiggly on the other?
That's supposed to be a hat.
Oh, okay.
Let's see. What are those percentages? 38 over 62. 49 over 61. So that is about 61% and 80%. For a difference, so like I could say that the difference in p hat of school minus the p hat of no school is a negative 0.19. Being believable so far? Tracking? Okay.
Yes.
I need to define what P means in this. I should have done it earlier. So like P is talking about the percent of kids who needed social service. So like P is percent kids needing social services. All right. So what's our null?
That they equal each other.
That they're equal. So like the true proportion of the kids who went to preschool equals the true proportion of kids who no school. So it's not P hat, it's P. So that means the true, the like actual number. And then our alternative does this provide evidence that preschool reduces the later need of it? So P is percent needing social services. So reduced would be like, we think that the school is less than no school. So percent of kids who were school reduced less than percent of no school, true proportion of no school. Alright. So I need to, I'm gonna go to a different page since I'm running out of space. The next thing I need to do on these two sample things is I need to get my P combined. Like I need to do that at the beginning. I need to get what I think the true proportions is. So I need to do 38 plus 49 over 62 plus 61. So like I need to get that combined value, which comes out to 71%. And so what this is our assumed true proportion of schooled kids and true proportion of not schooled kids. Like this, that's what this value will be for the rest of the problem, for the true P, the true P for both. It's just because there is no claim. Maybe I should have done that first. So like on a typical problem, we have a claim. Like I claim 92% of people want me as mayor of Bryan, because why not? And so that's like a claim. On this is sort of like our claim. We have to make this combined value to be our claim. So that's like what this value became. So maybe I'll say that first next time. Okay, I'm not gonna be lazy on this one. I'm gonna do my conditions to set a good example because we need to write them, because we have to write them, because they're on every rubric. But they're really easy. You just write it like this. You can just say, do you have random samples? And you would say, yes. And then, let's see, is 62 less than 10% of population? Is 61 less than 10% population? And that's like, yes, there's so many kids in the country, in the world, whatever. And then, is your sample size of 62 times this value over here, the claim, 71%. 62 times 29%. Are those greater than 10? So I actually use this value over here, the claim. And then is 61 times 71%, 61 times 29% greater than 10? And like those are checks, 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 checks. So we're good. So I can actually do a normal distribution, mean, standard deviation, all that. Like it doesn't have to be, the conditions don't need to be anything huge, just like, it's just like a nice little minute you have to take to write them down. Alright, so I need another page, a big problem here. So what I've got is, you don't have to write the mean, how about I just draw a picture here? So here's my picture. not the best one. So the mean, we think the two true proportions are both at 71%. So the difference between them is 0. That's the value 71 minus 71. And then we got a p hat of negative 0.19 because we did, what was it, 61 minus 80? That's that. What percent chance or less than did this have of happening? So that's kind of like my picture of what's going on. So I'm going to do a z-score of negative 0.19 minus 0 divided by, and then I'll do it in a different color, the standard deviation formula, which is like a little bigger and heftier for 2 samples. So you do what you assume the true proportion is times 1 minus it over sample size of 62 plus what the claim 1 minus the claim over sample size of 61. So yeah, these values, just what we're claiming there. I like to double check myself, so I'm gonna do it again in the calculator. Same answer, so that's good. Z equals negative 2.321, so 2 is good. So negative 2.32. Hope you haven't run out of room on paper.
Okay, we got like a whole half page.
Yeah,
so.
don't write too big, you know. Okay. So then get this value in a table, and then we're going to conclude what value is on the z table for this. I'll just tell me.
It is 0.0102.
Perfect. 0.102. Okay. And so it doesn't. We're just going to go under the assumption, it doesn't say an alpha of a certain level. So under that, we're just going to use alpha of 5% is like your baseline. So then let's make our claim. Maybe I do need to go to another page just to have enough room to write it up top. So like 0.102 less than 0.5. So that means I was too far gone. Like this picture, this value was unlikely to happen by chance. So that means that I have evidence for this. That I have convincing evidence that preschool reduces the later need for social services for children. So then you just write that, like all the way 4 pages later on the notebook. I have convincing evidence that attending preschool reduces the need for social services later. Boom. Did it. it's the same bones, like the same framework as the one sample, but there's just slight variations in the middle that like make it different because it's two proportions. So it does require some practice. That's why I wanted to do 2 problems, and then I've got some problems to try, and I wanted to do them in class so that, you know, when you try them out, you can fail at them and see how to do them right quickly instead of, you know, failing at them at home or something. I don't know. So I'm going to try these out, do the problems, and